Hello everyone, welcome back to our channel. We were discussing about complex numbers and quadratic equations from class 11th Maths NCERT. Now we know that we represent a complex number z by x plus iy, where x is the real part and y is the imaginary part. We also know that if you have x comma y as coordinates, then you represent them in a real plane of x comma y as something called a point whose x coordinate is x and y coordinate is y. Let this point be P. Here, x comma y can be considered as an ordered pair where your first value represents your real part and second value represents your imaginary part. If I were to plot this ordered pair instead of this one, the difference being here y is imaginary and x is real because it's connected to your complex number, and here x and y both are real values. So this plane can be called as a real plane. Let's represent x comma y from a complex number in a plane. If I represent all the real values of complex number z, we know that x and y individually are real values, but this is the real part and this is the imaginary part. So if I represent all the values of x over here on this x-axis and all the values of y on the y-axis, so all the values of x are represented here and all the values of y are represented here, then your x-axis would be a collection of real values, and your y-axis can be said to have a collection of imaginary values. Thereby, your x can be called as a real axis, y can be called as your imaginary axis. The plane initially was a real plane where x and y represents ordered pair of real values. Here, this plane, which represents all the complex numbers, will be called as an argand plane, or a complex plane, for the mere reason that any point in this plane, say this is a point in the plane, you can have a corresponding x value and y value, x1 comma y1. See, this point is x1 and this point is y1. So you're calling this as a complex plane for the mere reason that this ordered pair x1 y1 represents, say, z1 as a complex number whose value will be x1 plus I y1. So where you have real parts on your x-axis and imaginary part on your y-axis is said to be an argand plane and or a complex plane. Now, one second. In this particular plane, let's redraw it. Your real axis and your imaginary axis with x dash, x, y dash, and y. In this particular plane, let us consider a point P. You can join the origin with this particular point. Now we know that this particular point will definitely have its x coordinate and y coordinate. Let this distance be x and this distance be y. So the coordinates of P will be x, y. And the corresponding complex number will be z1 is equals to x, y. Sorry, z1 is equals to x plus iy. We know that OP line forms an angle with the x-axis. Let us represent this angle made with the positive x-axis by theta. This distance OP by small r. So these are our assumed notations at this moment. By observation, we can see that this x value, by observation, we can say that cos theta over here will be equal to adjacent upon hypotenuse, and sine theta will be equal to opposite side value upon hypotenuse, which means that your x is equals to r cos theta and y is equals to r sine theta. And we can represent these values of x and y in your P to have r cos theta and r sine theta as its coordinates. Now, by observation, we can also see that r, this is a right angle triangle and r is the hypotenuse, which means the value of r will be square root of x square plus y square by observation. So we have applied Pythagoras theorem over here to obtain the value of r. Since z1 is equals to x plus iy, we know that modulus of z1 will be equal to root of x square plus y square. From the figure, we know that root of x square plus y square is equal to r. So this value can be written as r. This r has a name. It is called polar coordinate. Polar coordinate. Now this is first polar coordinate. There are two polar coordinates. First one is r. Consider the angle theta. This angle theta comes in, this angle theta is the angle formed between OP and the positive x-axis. Now we have calculated the values of cos theta and sin theta. We have cos theta is equals to x upon r and sin theta is equals to y upon r. If you divide first equation with second, let's divide the second by first because it's more prominent or more used, people are more used to it. So dividing equation second by first, you get sin theta upon cos theta is equals to y upon r upon x upon r. So your r gets cancelled and you're left with y upon x. Sin theta upon cos theta can be written as tan theta is equals to y upon x. Theta can be written as tan inverse y upon x. Now this tan inverse is yet to be expressed or yet to be put in your books of 11th standard. They will be introduced to you in 12th standard, but it is pronounced as tan inverse of y upon x. Now this is the value that your theta angle holds, the angle between OP and positive x-axis. This theta is your second polar coordinate. So you have two polar coordinates, r and theta. Next. So you have seen that r can be also, now there are other names for these as well. R is said to be mod of z or mod of z. Theta is said to be argument of z. This is argument or amplitude of z. This is modulus of z. So instead of representing your instead of representing your r in terms of x and y, we can represent it in terms of r and theta. We know that z is equals to z1 over here considered. I've considered z1. Let's shift it to z. Okay. So z value is equals to r. Let's write it in terms of x plus iy first. And we know that from the previous discussion, where x is equals to r cos theta and y is equals to r sin theta. When we substitute these values here, r cos theta plus I sin theta, I into r sin theta, you can take r common to have r into cos theta plus I sin theta. Now this is the polar form or polar representation of your same complex number. Polar representation of complex number. Now, your theta value is an angle. This angle is measured in radians. Also, this theta value can be any value from 0 to 2 pi. Now, this is the interval that it holds. But we know that angles are allied as far as trigonometric functions are concerned. So your theta value can hold any interval with your length of where the length of the interval is 2 pi. So in general, we consider minus pi to pi as the principal argument, principal argument of Z. So this is the range that we consider. This is the interval that we are mainly used to. Let's see the difference. One second. So let's draw the values. Let's consider two scenarios where your theta lies between 0 to 2 pi, and second scenario where your theta is lying between minus pi to pi. Now observe we have written less than on both sides. Now just to include every value, we'll consider equals to on one of the two values. Now let us consider your x and y axis, and let's consider a point in each of the quadrants. So if you have a point P, let's consider them P1, P2, P3, P4. So if you have a point P1 in the first quadrant, you can say that OP is your value of R. In both, where your theta value, now theta value in first scenario starts from here, theta, and ends till here, till 2 pi. You're starting from here and ending over here. Here, you're starting with minus pi and ending to pi. Theta value is always calculated from positive x-axis. So this is your theta and this is your theta. Now, if you consider a second scenario, you can consider your point P to be lying in the second quadrant. If it lies in the second quadrant, the values of theta will be same for both the scenarios here as well. theta is calculated from positive x-axis, and this will be value of theta, and this will be your value of theta. If your point P is there in second quadrants, for both the scenarios, your value of theta remains same. It is calculated from positive x-axis. What happens if you are in the third quadrant? Now, in the third quadrant also, if you're calculating from 0 to 2 pi, you have to start from the positive x-axis and go anti-clockwise direction. However, in the second scenario, you will go in clockwise direction to reach the smallest value or shortest distance, shortest angle that is formed between your radius and your positive x-axis. So here your theta will be calculated in counterclockwise direction from positive x-axis, but here in this scenario your theta will be calculated from positive x-axis in the clockwise direction to form the shortest angle. What if you have it in the fourth quadrant? Here theta will be calculated from here till here, and here it will be a clockwise direction from positive x-axis. This is the difference, or this is the different values of theta that will be obtained from in the principal range or the principal argument of Z and in any general other value or the standard value you say. Next, let's consider some properties of argument or argument of Z to the power n. So Z is any value x plus iy, and argument of Z to the power n will be n times argument of Z. Second, argument of Z1 upon Z2 is equals to argument of Z1 minus argument of Z2. Now, we know that 1 upon Z2 can be written as Z2 conjugate. So this can be written as argument of Z into Z1 into Z2 conjugate. So anywhere where you find argument of argument of one complex number multiplied by conjugate of second, it literally means argument of first divided by second complex number. Third, argument of multiplication of two complex numbers Z1 and Z2 is equals to argument of Z1 plus argument of Z2. Now these formulas might look confusing, but we will look into the questions related to every formula or every topic in every topic that we are discussing. I'm just covering the theory first and later problems. So I think these are the basic formulas that's sufficient. Rest would be much more standard. If we do encounter them in RD, we will look into it. But right now, these are sufficient from your textbook and NCERT exemplar perspective. Next, let's consider the relation. We know the modulus of a complex number is equals to the distance of a point in the eigenplane of that complex number with the origin that we just studied here. R is equals to modulus offset. So this is the relation between modulus offset and your in the eigenplane, or the practical distance or practical meaning of modulus offset. What about conjugate? Let's understand that first. So in your xy plane, if this is your point P, then this can be your value, which is x comma y, and the corresponding z will be equal to x plus iy. Now we know that x conjugate is equals to x minus iy. If you want to form the point, say p dash for this, it will be x comma minus y. If you plot this point over here, this is the point p dash x comma minus y that you'll attain. You can join this. As you can observe, this, your r remains same, and this distance y, this is your distance minus y, which means your p and p dash are mirror images of each other. If they are mirror images, considering x as the mirror, so you can say that your z and z conjugate are form mirror images on the Argand plane. Next, let's have Euler form. We have studied two forms. Z is equals to x plus iy. Z is equals to r cos theta plus I sin theta. Another form is, now this is without any explanation. We discussed the explanation for the second form, but the third form will directly represent it, and we will not we will not discuss how we came up with this formula. We'll only understand that this is called as Euler form. Because the derivation, I can give you the derivation, but the derivation of it is beyond the scope of 11th standard. So this is called Euler's form. And thereby, by comparing these two forms, you can come to a conclusion that e raised to power I theta will be equals to cos theta plus I sin theta. Now, for some reason, if you take the negative of theta, so if theta is suppose equals to minus alpha, so putting it in this particular equation A, you'll get e raised to power minus I alpha will be equals to cos of, wherever theta is placed on the right hand side, you'll replace it by minus alpha, because that's the substitution we are considering. So sine of minus alpha, this will be equals to cos of minus alpha, minus of any angle is equals to cos alpha, because this is in fourth quadrant where your cos is positive. Sine of minus alpha has to be minus sine alpha, so this value will be negative sine alpha. So by this, we came to a conclusion that e raised to power I theta is equals to cos theta plus I sin theta, e raised to power minus I. You can even write theta. So e raised to power minus I theta is equals to cos theta plus I minus I sin theta. So these equations A and B are important, and Euler form is important. That you should know that your complex number can also be represented in the form of exponential. Now, the term exponential e is also yet to be introduced. We will introduce it after say two subjects. No, two topics. In this respect, there is a proof that we can discuss here, maybe. Let's say I is your iota. What if I take I to the power I? What will be this value? Your iota to the power iota will be what? You can use Euler form to come to the conclusion of this problem easily. I, your base, this is your exponent. So base can be represented as 0 plus I into 1. This here, comparing it with this equation C, we have cos of something should be 0 and sine of the same angle should be equal to 1. So cos of theta is equals to 0 and sine theta is equals to 1. You can have theta is equals to pi by 2 by observation. So cos pi by 2 plus I sin pi by 2. This value can now be written in Euler's form as e raised to power I pi by 2. This is the value of I. So I to the power I can be written as e to the power I pi by 2 to the power I. By laws of indices, your powers get multiplied, which is e to the power I multiplied by I multiplied by pi by 2. I into I is I square. I square is equals to minus 1. So your value becomes e to the power minus pi by 2. So as you can see, I to the power I leads you to a value which does not have any I term. So this is purely a real value. And the explanation of this was given because it's related to Euler's form. We'll now start with the second part of the chapter, or the theory part of the second part of the chapter, which is quadratic equations. Now, quadratic equations we know are represented by ax squared plus bx plus c is equals to 0 in general form, where a, b, c are coefficients of x squared, x and c is a constant term. The solution of this will be x is equals to minus b plus minus root of b square minus 4ac upon twice a. If the value of discriminant d, which is b square minus d, which is equals to b square minus 4ac. If this value of d is positive, it's well and good. If it's 0, it's okay. But what if this is negative? Now we are considering only one situation where your d is negative, where your d is less than 0. So if your d value is negative, definitely your b square minus 4ac will be negative. If this is negative, we'll rearrange this, and can you take minus sign common over here? Minus sign common, 4ac minus b square upon twice a. Now, if this is negative, definitely it means this value b square is smaller and your 4ac is bigger or larger. So if this is your larger term, 4ac, and you've taken minus sign common, so in the bracket, this value is larger and this value is smaller, definitely your bracket term is positive, forgetting about the outside minus. In the bracket, the value obtained will be positive. What happens here? Minus b plus minus, you can write this as root of minus 1 into root of 4ac minus b square upon twice a. This root of minus 1 value has to be equals to I. This is your modified version of original quadratic equation. So if your d value is 0, all you have to do is, instead of using this equation, you will finally resort to using the last equation, this one. Now this is your new equation only for d is negative. And your original equation, you'll use it when d is equals to 0 or d is positive. This equation is valid, blue one is valid only for if d is greater than or equals to 0 for two scenarios. Next, there isn't any other explanation given in a text for quadratic equations, but we will study only one property or based on it. The property so states that in a polynomial, say p of x, if you have a polynomial with you, then this polynomial will definitely have some real coefficients And let's consider this polynomial to be of degree n. So you have a polynomial, or you're considering a polynomial. You're making sure that the coefficients are real. Coefficients means the constant term attached to each before variable in each term. Constant value attached to each variable in each term. So if these coefficients are real and the degree of the polynomial is n be any number, any whole number, then this particular value p of x may have complex roots. That's a possibility. This possibility arises based on the values of your coefficients. Now, if it does have complex roots, then say z is a complex root, z is equals to x plus iy. And if this z exists as a root, as a complex root of this p of x, then the condition states that z bar will also be a root of this particular p of x. So the condition is, these are the standard conditions. If these condition persists and this is a root of p of x, then this will, or z bar or conjugate of z will also be the root of p of x. This is the property. So if you have z as a root, you'll have z bar also present over there. If you have z bar present, you will have z as well, because we know that conjugate z conjugate of conjugate will give you the original z value. So this concludes your theory of this chapter. We will start with the next chapter in the next class. Thank you.